I'm Katie McKighton, and this is Physics 2212, Lab 2, Magnetic Dipoles. As an introduction, the purpose of this experiment is to visualize a magnetic field, determine the relationship between the distance from and magnitude of a magnetic field, and measure the distance dependence of a small, powerful bar magnet. There are a few concepts and models that were used in this experiment. The first is the Biot-Savart law, which gives the magnetic field of a material using the magnetic constant, the distance from the object, and the magnetic dipole moment of the object. Next is the distance dependence equation that also can be used to find the magnetic field of the magnet. One model that will be used is the magnetic field of a bar magnet, which runs from the north to south end of the magnet and highly resembles the electric field of an electric dipole. As a preview of the results, from the distance dependence equation, n is equal to negative 3.46, and the magnetic dipole moment of the bar magnet was found to be 1.135 amps times meters squared. The system in this experiment was the bar magnet, and the surroundings were everything else. Initially, we had the bar magnet and the uncalibrated magnetometer. To calibrate the magnetometer, the location of the magnetometer chip was determined by sliding the phone horizontally and vertically in relation to the ruler. The bar magnet was at one end to find at which position of the phone relative to the bar magnet read the strongest magnetic field. The location of the magnetometer chip was then used to determine the relative distance from the magnet to the reader. The on-axis distance from the magnet and the reader that yielded specific given x components of the magnetic field were found and recorded. The distance dependence equation was then used with these results, as these values were linearized by taking the natural log of each side. The graph of these linearized values is shown below. Lastly, the off-axis B field of the magnet was found by placing the magnet at a certain distance perpendicular to the magnetometer. The field of just the Earth was recorded before adding the magnet, which was used to correct the measured values. Finally, the magnitude of the net B field was calculated by Pythagorizing the x, y, and z components of the B field of the magnet that was found. When the magnet is far from the magnetometer, it measures a close to, but not zero, magnetic field in the x direction. This could mean that there is another magnetic field affecting the magnetometer from other objects in the room. As the magnet moves closer to the meter, the x component of the field increases, and the position of the phone impacts the readings. This is due to the magnetic field of the Earth and the location of the magnetometer chip. First, I used the distance dependence equation along with the graphs composed by the data to determine n and k in the distance dependence equation. Then I set the right side of the distance dependence equation equal to the right side of the Biot-Savart law and plugged in known constants and calculated values to calculate the mu, the magnetic dipole moment of the magnet, which was found to be 1.135 amperes times meters squared. Next, I created a model of the magnetic field of the magnet using GlowScript. I used the value I previously calculated for mu and determined the magnitude of the B field at different distances, both perpendicular and parallel to the magnet. Lastly, the code determines the B field at a 45-degree angle to the axis of the magnet. The picture on the right side is a created model of the B field, where the orange arrows represent the field on axis, the blue arrows represent the field off axis, and the purple arrow is the field 45 degrees from the axis. The theoretical off-axis field was calculated to be 1.425 times 10 to the negative 5 teslas. The experimental off-axis field was calculated to be 5.766 times 10 to the negative 5 teslas. The 45-degree field was calculated to be 2.69 times 10 to the negative 5 teslas. A bar magnetic field can be modeled as a magnetic dipole. Here, the choice of model should accurately represent the field of the magnet. One potential source of error would be finding the magnetometer chip imprecisely, which would lead to incorrect magnetic field readings. Another potential source of error could be other magnetic fields interacting with the magnetometer. I could not conduct this experiment outside, so it is likely that the magnetic fields of close-by objects, such as my laptop, may have interfered with the results. If the setup had not been oriented to compensate for magnetic north, the magnetic field of the Earth would have greatly impacted the readings. I could have compensated for the Earth's magnetic field in another way, such as by subtracting it from the measured values at each distance. If two magnets stuck together had been used, the recorded measurements would be about doubled, but the direction of the fields would remain the same.